Hello, how are you? In this video we will see are most computable numbers rational or irrational numbers, and why. And I welcome you to the Question Answer channel, the channel where you will find the answer to everything. Thanks to Nathan Hannon, Justin Rising, James Buddenhagen and Danny Kodacek for sharing their answers to this question with us. The first answer will be from Nathan Hannon.
Both the rational numbers and the irrational computable numbers are countably infinite. However, there is one sense in which we can say that most computable numbers are irrational. The computable numbers form a vector space over the rational numbers. We can think of higher dimensional vector spaces, or affine spaces, over an infinite field as being much larger than lower dimensional ones. For example, a plane is much larger than a line, even though they have the same cardinality. A couple of reasons why this makes sense. You can fit infinitely many disjoint translations of the line inside the plane. You can also map infinitely many copies of the line into the itself, or even the plane into the line, bijectively, but you can't do this with nice operations such as translations. If the line is embedded in the plane, and you choose a random point in the plane in a reasonable way, it probably won't be on the line. For example, if you choose the coordinates, in some basis, independently according to some continuous distribution, it has probability, math, 0, math, of being on the line. If you take a line away from the plane, what's left is still much larger than the line, in this sense. The computable numbers form an infinite dimensional vector space over the rational numbers. The rational numbers, within the computable numbers, are therefore analogous to a line embedded in an infinite dimensional space. The geometric analogy falls apart when you start dealing with vector spaces over the rational numbers, but you can still make similar arguments. You can fit infinitely many translations of the rational numbers within the computable numbers. Choosing a random computable number is tricky, but if you do it in a reasonable way that isn't specifically designed to favor rational numbers, the probability of getting a rational number will be small, i.e., will approach 0 as you increase some parameter. So it makes sense to say that most computable numbers are irrational.
The next answer is from Justin Rising.
In order to answer this, you have to define what you mean by most. There are a few typical ways to describe how large a set is, and by all of the ones I can think of off the top of my head, neither set is larger. Let's examine them one by one. Cardinality. This is the most common notion, and by far the coarsest. The rational numbers are countable, and all computable, and the computable irrational numbers are countable as well because the set of all finite length programs is countable. Measure. The next most common notion is that of measure, which is a generalization of notions like length, area, volume, cardinality, and probability. Countable subsets of the real line always have measure 0, so there's no difference there. Density. If one set is a dense subset of its ambient topological space and another isn't, it's reasonable to call the dense one larger. The rationals are dense in the reals, and you can find a proof of that in pretty much any analysis textbook. You can mimic the proof to show that math BB, plus SQRT, 2, math, is dense as well.
We can continue with James Buddenhagen's answer.
Are most computable numbers rational or irrational numbers, and why? The computable numbers are denumerable. See for example Turing's 1936 paper. Closing parenthesis dot. The rational numbers are denumberable. Both are infinite sets, so they have the same cardinality. Since, for each positive integer say, n, which is a rational computable number, there is an irrational number. n2, square root, n2, an irrational computable number, one concludes that it is not the case that most computable numbers are rational, and it is not the case that most computable numbers are irrational.
We can continue with Danny Kodacek's answer.
Obviously the number of both rational computable numbers and irrational computable numbers is infinite, so the question is really whether the size of the set of irrational computable numbers is countable or uncountable. The answer is that it is countable, since you can use Turing numbering to count them. All computable numbers are, by definition, able to be computed using a Turing machine program or similar finite state machine, and it's possible to assign each of these programs a unique integer so they can be placed in a countably infinite list. So both the rational and irrational computable numbers are countably infinite, and so there are the same number of each.
This is the end of the video. Thank you for staying until the end. I hope the video has you more. If so, you can subscribe and activate the bell to miss any video. Also remember to leave a like. We are coming to the end of this video. Share your views on this question in the comments. See you next time.